Hey, welcome to the iCanX Youth Talk for today. My name is Michinao Hashimoto, and then today we are going to, I'm going to introduce the amazing two talks and then panel discussion for the youth talks. Hey, let me first introduce myself. My name is Michinao Hashimoto from Singapore University of Technology and Design. I'm currently associate professor focusing on the microfluidics and 3D printing. Then today I'm excited to hear amazing talk from different places, regarding the additive manufacturing, especially focusing on the 3D printing. So, here is the talk. We do have four speakers. Four people involved here. Myself, and then first speaker is the Professor Zhangwei Chen from Shenzhen University. The second speaker is the Professor Shaoying Huang from Singapore University of Technology and Design. And then after that, we are going to move on to the panel discussion, where we are going to have the presence of the Professor Tian Kong from Shenzhen University and also myself. So let me introduce and then start the first talk. The first speaker is the Zhangwei Chen from Shenzhen University. Okay, and then Professor Zhangwei Chen is the currently a full professor and the director of Additive Manufacturing Institute at Shenzhen University. He is a distinguished scholar of the university, currently as a leading scientist. He has won the first prize of the Shenzhen Natural Science Awards, the second prize of the Guangdong Natural Science Award. He earned his PhD from Imperial College London in 2014, and his master degree from Xi'an University and then École Centrale de Lyon in 2007. His research focuses on the EAM of the high-performance materials, and he has published over 140 papers with a citation over 6,000 times. 9 papers are highly cited. Okay, and then he currently serves as a board member of the AM Materials branch of the Chinese Materials Societies. So with the many achievements that he has, we need probably 2 hours to actually introduce everything. So I think this is the today he's going to talk about the 3D printing of the inorganic materials. So please get ready, Professor Chen, and then whenever you're ready, please get started.
Yes, thank you for the introduction. Moderator, thank you very much. And I like to share with you guys my documents, okay? The slides. Is it okay? All right. So thank you for the introduction. And my name is Zhangwei Chen from Shenzhen University Additive Manufacturing Institute, and I'm glad that I'd be honored to be here and be invited to give an introduction and also the lecture regarding the additive manufacturing of inorganic materials. So first of all, I will introduce this is a table of contents, and first of all, I'm going to introduce the Additive Manufacturing Institute in Shenzhen University. Well, we have over 60 students, and also including the PhD and the master student, and 7 postdoc, and we have 6 member of staff for the team, and we focus on the polymers, ceramics, metals, and composites, and so on. We use stereolithography, including digital light processing, and inkjet printing, low temperature direct ink writing, SRM selective laser melting, and so on for the equipment side. And the application side is the electrode for the lithium-ion battery, and also for the SOFC. For catalysis using nuclear fusion and some other structural components use aerospace industries and so on. So we have a very close collaboration with Osaka University and other universities over the world. This is a group photo 2 years ago. So you can see that we do have some students from other countries like the Nigeria, India, Pakistan, Asian countries. So they do their PhD in our institute, and then when they finish, they go back to contribute their own force to the industry in their country. So we have some sort of homemade devices, equipment, including the DRP machines, 3D printing machines, and also DIW, direct ink writing machines, and some other metallic components, SRM machines, and so on. And considering the material side, we do prepare our own slurries, including the milling, particle size distribution, drying and sintering, debining, and so on. We after printing using our own equipment, then we have some characterization facilities, including the SEM and mechanical testing based on our own institute. If we do have some sort of like XRD, FTIR, then we go outside for the larger facility on the campus, as well as Shenzhen City facility, shared facility. So a basic introduction to the inorganic and ceramic 3D printing. You know that when I'm talking about inorganic materials, basically we are more focused on ceramic materials. So in the 3D printing industry, the Smart Tech, the company has a the prediction regarding the future total market in 2028, there will be like 7 times higher than the revenue for the all industries in the ceramic AM. So we have high-end hardware, including the devices, equipment, and we have technical materials and technical components, including the final parts after sintering. We do have for the ceramics as well. And although this is a very small research area, we can see that still there's lots of increasing profits we can earn from the industry. And 3D printing, people are often talking about 3D printing for a long time, and it's not a straightforward or one-step thing. So we do 3D printing in terms of shaping, and beforehand we do the design, the CAD modeling, and there's a drawing of this aqua-based material, and then we do heating. So heat treatment is mostly the very important part in the shaping and 3D printing of ceramic or inorganic components. That includes the debinding process and also the sintering. So basically, they are working at high temperatures. So shaping, 3D printing, and heating, including debinding and sintering, these 2 steps are the most important step that worthwhile for research in inorganic ceramic AM. So we were honored to have this paper published in Journal European Ceramic Society. There was a review paper. I was the first author and the corresponding author, 3D printing of ceramics review. And now I think that's about like 1800 something. Yeah. So I did a very quick calculation. It's almost like starting from the application year, and every single working day there will be 1 citation. So it means that people working on that, and also we are working hard on this kind of topics, so that although it's not well known to other people, 3D printing of ceramics, but still it's worthwhile for the research and study. Inside this paper, we characterize like 10 types of 3D printing terminology, starting from liquid, ink, slurry, the liquid-based material. And secondly, we do have powder-based material. And thirdly, we have the bulk materials. So people may be most familiar with stereolithography-based techniques, like the SL machine the printing process, and also there's DLP, and now this is the most advanced one, and we are focusing on as well. And there's also 2-photon polymerization, and I think this one is quite interesting. The direct ink writing, people working on that very widely. and because this is easy to handle and easy to use as well. And now there will be sort of like binder jetting, which coming to become more and more popular. And there are also SLS and SRM, which are better for metal or polymers, but still for ceramics, there are some difficulties as well. And if you are interested in this paper, then you can scan this code and see download very easily and freely. There's no charge for that. And I demonstrate here as well. The outer circle are some of the components we basically made in our own institute, and I'm showing this for the purpose of, you can see that this is very concise and delicate structures we have fabricated in our institute. And the inner circle, they are some sort of very special components made by other types of materials, but they are they are sort of precursors material, which are quite different in color, in terms of color for when compared with the outer circle ones. So these are the outer circle are more for the oxide ceramics, and the inner circle are more for the inorganic materials, which is polynary materials like SiOC, SiNC, and so on. We have a silicon carbide as well. So I will explain these in more detail later. Yeah, so first example is cauterized ceramics by polymerization. Well, this ceramics is normally conventionally made by extrusion kind of molding, and the material is basically for the purification of the exhaust from the fuel vehicles. And the conventional method is using the molding by extrusion, but 3D printing may be a good method when it comes to the highly complex structures. And people already try with the different sorts of 3D printing technology like the SRM, DIW, but basically you can see that some of the features are not that satisfying. So I was, proposing this kind of technology using a DRP, photo polymerization, for the fabrication of this kind of components as well. And starting from the commercially available powder, cauterized powders. Well, basically for cauterized powders, they are sort of a mixture of different kinds of oxide ceramics, and starting from these powders, we hierarchically disperse powders inside these slurries. That we made our own slurry from following this kind of recipe, and using our own machine, starting with the DLP. This is the exposure of the UV light, so that we can have a sort of photopolymerization underneath, and the components, fabricated part, printed part, can be elevated from layer by layer. Yeah, that's called 3D printing. And then we test all sort of the slurries made, starting from R1 to R8. Then you can see that maybe R7 is too solid, so we are not demonstrating here. And you can see that the sedimentation, that's something relevant to the viscosity of the basic parameters for the slurry characterization. So the R1, you can see from upside down that R1 is not a good one, and R8 can be regarded as a good one or best one, the best one. So it can flow very easily up to like 100 days of sedimentation settling down. So we use R8 as a proper slurry, and starting from this kind of slurry, then we examine the curing thickness and penetration depths and all sorts of information needed for the printability. We call printability is the quality of the printing, and the quality of printing includes the single units, like the holes, like the single lines, single walls, the thickness, and so on, layers as well. So if everything's good, then we start printing. And the printing is sort of optimization, topological optimization, and it's the optimization oriented design. So we starting from our own the aims for the design. Then, for example, if you can get if we see some sort of a high velocity, then we will contribute concentration of sort of the channels over there, and getting a highly dense channels. So this is not feasible with the conventional technology, because using the molding, then you need to take time or money from the molding itself. Then we try with 3D printing. It's easy for us to have a highly flexible design, and especially we can have like a sort of interconnected structures, very highly complex structures we can fabricate using 3D printing technology. And these are some of the results we have here. And still we are working on that, maybe doing some tests over the vehicle, and this is still in progress. Hope I can give you some other results in the near future. And the second example is a lithium silicate silicate tritium breeder by photopolymerization, 3D printing as well. And the background regarding this project is very interesting, because you know that nuclear fusion is commercially available, and all sorts of nuclear power stations now are based on nuclear fusion. And there's another one called nuclear fusion. So nuclear fusion is the isotope of the hydrogen. We have a deuterium and the tritium. So the deuterium is very easy to get accessible from nature, and abundant of resources from nature, especially from the seawater. And we don't have too much tritium actually in nature, so we have to produce our tritium based on the lithium-based ceramic pebble. Okay, we stack the pebble into a pebble bed, and then we put them into the reactor. Then there's a flow of neutron. Okay, the flow of neutron coming into they have a reaction with the lithium also silicate pebbles. So it comes to the end with a sort of generation of a tritium. So we call this as a tritium breeding zone. Okay, tritium breeding, it means that we produce tritium from that kind of facility. There are basically two types of difficulties or challenge from this kind of configuration. First one is because the pebble is round shape, so the spiral shape pebbles, they have a sort of point contact. When at high temperature, like up to 800 degrees C, there will be sort of stress concentration. Then the failure of the structure come to be a very easy thing. And another thing is because of geometry, stacking. So there is a limit, like 70% of stacking ratio. So we cannot go even higher. Then there's a problem with the increase of tritium breeding efficiency. So these two main disadvantage of the drawbacks. So we have to face on that, and people working hard on this kind of issue. And we have tried proposing using the original powder, and fabricate our own recipe of slurries. And then we use an entirely different configuration. This is a lattice structure, no longer pebble bed structure. So we have a lattice structure. We print our own lattice structure, and for the use in the tritium breeding facility. And then the fabrication of the slurries, they are all the same as the cauterite ceramics. But here we have another method as well. We use generative shaping and material forming, so we call 创新创造 in Chinese. And the problem is because the lithium oxosilicate, they are highly expensive and not commercially available. So we try very hard to fabricate the small batch of lithium oxosilicate. That's very limited amount, and very expensive, not commercially available. And the most important thing is sensitive to CO2 and the HO2. So we're not easy to manipulate with this kind of material. Then we try with A plus B. So A plus B means that we use low cost material, a combination of this one with silica. Then we try with the mixture of this kind of slurry. So there's no longer sensitivity towards the environment. There's low cost and abundant resources, very simple processing, and at high temperature, because we when we after finish the slurry, then we do 3D printing. Okay, so this is called generative shaping. We make the shape. Then afterwards there's high temperature sintering either way. Okay, so with the original powder or with the A plus B, so it always need to go higher temperature. So at high temperature like 1000 degrees C, so there will be a generation of lithium orthosilicates. So this is a very good strategy that allowing us to get very quick and low cost processing. Then, of course, using 3D printing, you have sort of a highly flexible design, varied packing density starting from like 40 to like 80 now to sort of 90% for this kind of porosity, gradient structure design, and so on. And another thing is also we try with A plus B using organic and inorganic components for both. Okay, and the one on the left hand side is A plus B. They are inorganic, and we have inorganic plus organic as well. So both routes they are feasible and they are working quite well. So they have very good, nice results, especially in terms of the packing fraction. We remain the same packing fraction, but we have a higher effective electron modules and so on. And also we examine the possible influence in terms of the shape as well. So the sphericity for this kind of round shape beads also will produce. Then they have a very nice geometric features as well. And of course, when we try with 3D printing, people may know that during 3D printing there will be sort of a staircase effect. If we are using this kind of method, then there will be no longer staircase effect. This is because of the flowing of this kind of leaky phase when at high temperature. So this will get rid of the staircase effect, get rid of the surface roughness, and there's no longer the property in terms of anisotropy. There will be isotropic kind of properties. So this kind of strategy can be very, very efficient and useful for producing the chitin breeding units. And also, you see there's some of the results. The surface roughness is getting reduced as well, and this is all due to the reaction process at lower temperature, and the surface roughness is reducing like 70% compared with traditional methods. And then apart from that, we try with the dual phase components. The aim is to get the higher, relative density and also smaller grain size for better crushing load. This is the mechanical properties we need to get. And we aim with 1+1 much larger than 2. So this is called dual phase components, including the titanium and the silica as well. And as a conclusion for this part, so we design our own lattice structure for 3D printing, and this overturned the pebble bed configuration used in conventional strategy. And we also design a very good image for this kind of process, starting from the bulk porous, naturally porous structures, and then using pebble bed with original powder, then with the lattice structure starting from the original powder by using 3D printing. Finally, we have reaction sintering using GSM strategy. So interestingly, the overall performance getting increase. So this is something relevant to the strength versus the structural engineering, which has some sort of benefits based on the GSM strategy. So we get some national media coverage for this kind of results, also with international media mentions and so on. Then there's another very interesting material is silicon carbide ceramics by photopolymerization. For photopolymerization, the problem is because the UV light should be absorbed by the resin, and we intend to get the much more absorption for the resin compared to the powder, because the powder doesn't change overall for this kind of process, and they are embedded in the photo linkage, the photopolymers. So we don't want silicon carbide to absorb so much energy, so much light, but they do have a sort of a high light absorption. So we don't want that. And then what we do is we propose a kind of strategy, pre-oxidation. And this kind of process getting very, very tiny little bit of coverage, of pre-oxide material, like starting from silicon carbide. Then we have silicon oxide. This is silica layers. So it's kind of a shell kind of structure, and if we have this kind of coverage of the coating, then we can very easy increase the penetration or curing density, curing performance, starting from like 40 to like 80 and 100 micron. So the penetration depths increase, then we have the chance to getting the overall performance of the printability getting much better, and these are some of the final results we get for the 3D printing of silicon carbide. Normally, if we don't do that, then it's hard to fabricate the 3D microstructures. These are some of the results as well, starting from the printed results, and we have a sintered results. So they both work very nicely. And you can see this one, we do have some sort of very interesting features that they are concise and delicate and very, very high resolution. So this is something we want for kind of advanced applications, especially for the the microwave shading, and also the protection from the fire and high temperature as well. So there's another interesting method is polymer-derived ceramics by photopolymerization. The inorganic material can be fabricated from a pre-ceramic polymer. That's kind of very interesting phenomena. So we start from polymer, then it become inorganic material like ceramics. So this is something published already in 2015 by the Lawrence Livermore, the U.S. National Laboratory, and they use this kind of UV curable of the photo ceramic polymer, then using photopolymerization 3D printing to get the the green parts. Then at high temperature, 1000 degrees C for high temperature pyrolysis, we can get the polymer-derived ceramics. So this is very interesting procedure, and there are some benefits. So first of all, there's low cost. It means that there's no, the involvement of kind of ceramic powder inside this kind of slurry, because when you do with ceramic powder, then there will be the very hard for this kind of high viscosity leveling. If you don't level quite well, then it's hard for the printability. The printability become lower. Then if we use this kind of material, we no longer need a scraper. We don't need to manually level the slurry so that we can print them, and it's soluble inside these kind of inorganic components, so they will be like totally liquid. It's like a resin. Okay, so this is the one of the most important advantage we have, and controllable in terms of molecular level. We can dope kind of metallic components, metallic elements like ferrite, zirconium, and also titanium, so that they can increase their mechanical performance. They can have a sort of microwave and magnetic properties and so on. So this is very interesting, and the process is very easy. So it's like I mean, during 3D printing is totally the same as the resin 3D printing, liquid phase, and no longer involvement of powders, and we the only thing additional step is the high temperature pyrolysis. So we need to, like sintering, you have to remove or get transformation from polymer to ceramic or inorganic material, then you have to put in high temperature. So basically, we modulate our own first, recipes, and this is basically something relevant to the chemistry side, and we try with much of our effort to control the molecular compositions and so on. And then we try with the same thing as the slurry. We try with the identify or measure the viscosity, measure the penetration depths, and also the exposure energy, TG, to see how much you can get from the, this is called the ceramic yield. So how much you can get for the final solid. It's normally like less than 40%. So you will encounter lots of shrinkage during the whole process at high temperature. So these are some of the results we got like two years ago. Especially, you can see that starting from the starting from the printing, we can get this is a UV light printing, and then we can get very easily the red like a polymer kind of components, 3D lattice structure. Then after high temperature pyrolysis, then we can get a very large shrinkage, and it become dark shape. So it's a kind of non-conventional ceramic composition. We have like SiOC or zirconia OC and so on. So these kind of structures are not the same as the oxide structures we produced earlier with corduroy or even like SiC and so on. Yeah, then we also can design our own, the hierarchical porosity, starting from the CAD model, like the, starting from design, and also starting from the both the high temperature treatment as well. You can get some sort of hollow structures inside this kind of structure. Then the aim is to have high strength and low density. The high strength realized by hierarchical porosity. The low strength, low porosity. Low density. Aim realized by the hierarchical porosity produced either by the design and also high temperature sintering or pyrolysis, and high strength by the pinning of zirconia and titanium. So there will be a mixing of the molecular level in the ceramic body. Then there will be sort of enhancement in terms of mechanical properties. Some of the results we have comparison with the other type of similar materials. Then we can get even higher performance. And also we try with some sort of new strategy, because this kind of material, they are very hard to get bulk solid kind of highly dense structure. Then we need to try with the strategy how we can convey, how we can make the the evaporation or the removal of this kind of inorganic organic material during lower temperature, less than 600 degrees C. So we try with opening small channels with a low melting temperature for this kind of additives. Then we are succeeded in making small channels before the overall evaporation and removal of the rest of the organic components. So there will be no cracking, there will be no much shrinkage. The shrinkage is much uniform, and the cracking is eliminated. So we compare these with other type of material as well. We can see that we got sort of a high thickness and also larger size. So these are some of the contributions we made with the composition adjustment. And also, we published 2 papers as a review papers in Progress Material Science for additive and polymer derived ceramics with Paulo Klopper, who's a very famous professor in this kind of field. And also, there's a front page journal paper in Journal of Inorganic Materials. So this picture, I designed this one. So it's very visible that people can know starting from this kind of image. So we expose our UV light onto the liquid precursors resin. Then we get the green part, a lattice structure. So this is solid from liquid. Then at high temperature, like 1000 degrees C, there's a high temperature pyrolysis. So it become ceramics, inorganic material. And we have a larger background is aerospace, so there will be sort of microwave protection, high temperature protection for this kind of specific composition for the ceramic material. And as a summary for this part, so we, starting from inorganic material, the targeting ceramic powder, we use 3D printing as a generative shaping. So we only make shape. There's no change along the processing of the material side, starting from slurry, and then do 3D printing. There will be sintering. So there's almost zero difference for the powder. There's no change for the powder, but we propose a GSM method. So it means that for some sort of ceramic or inorganic materials, there will be highly sensitive or hard to get. There will be no resources for that kind of materials, and not commercially available. Highly sensitivity for the in terms of environmentally sensitivity. So we use kind of a GSM. So SM, the M is for the material forming. It means that there will be a generation of producing material from the high temperature sintering. This is in fact the reaction sintering. So we propose like inorganic plus inorganic, so A plus B, they are both inorganic material, and one can be inorganic, another one can be organic. So the last one is they can be entirely organic. So this is polymer derived ceramics, and these two are like the one we made for the nuclear fusion, and some of the examples I have shown earlier. So we propose this kind of strategy. Actually, the method is not entirely new, but we propose or summarize this kind of strategy so that it can be kind of widely applicable for all sorts of highly sensitive materials and not commercially available materials or other type of materials that can be used for this kind of strategy. And also we fabricate our own machine, and this machine is high speed wet photopolymerization 3D printing machine with high speed and high resolution. Because there's a sort of oxygen inhibition zone. I mean, this kind of chemical term, so that it can move very, very quickly, freely, and there's no longer leveling, there's no longer posing. So it's like magic. You can just get the object lifting from the wet. And there's of course the exposure of UV light underneath. And why we build this kind of machine is because conventionally for DRP machine the speed is very, very low because of the additional processing like leveling and posing and so on. So we use this kind of machine because we want to not only like make our commercial resin possible, but also for the polymer derived ceramics and also for the slurry ceramics possible. So there are two benefits. One is there's less, surface roughness. Yeah, no more staircase effect because there's like zero thickness for the layer. for the layer. This we would call layerless. There's no layer actually compared to the DLP conventional 3D printing technology. And this is the first thing. And the second thing advantage is because of no layer, there's no layerless production, then there's no longer the anisotropic properties inside the structure. So the surface roughness getting better, and the overall isotropic.
Okay, Zhangwei, please use your time. Okay, you use out all your time. Okay.
Sure. I'm going to finish. Yeah. So this is very easy to understand, and the benefits we can get. Yeah, quickly then we also fabricate using the inkjet printing for SOFC electrode and electrolytes, and make our own ink similar to previously discussed components. And this is a very good strategy for making the thin layers, also the bulk layers, and also the porous layers, very thin, down to like 5 micron. And we examine the relationship between the porosity and the mechanical performance. And this final part is the lithium-ion battery we made with the DIW. We design and make our own homemade machine. This is low temperature DIW down to minus 40 degrees C. Then we can keep, it's like free drying. We can keep the microstructure, pore microstructure, so the mechanical and also the electrochemistry performance can be enhanced. And we make our own package of the graphene based full batteries, and also the electrodes with the different design and compositions, and test them. And these are some of the very recent results. Yeah, I think that's all. I don't take time to have the conclusion. Thank you very much. And we also hired some very talented PhD student and also postdoc to work with us. If you are interested, just contact me with S Chen at Shenzhen University and edu.cn. Thank you very much. Thank you. I'm sorry for the time. Maybe, yeah.
Thank you very much, Professor Chen. This was great talk. So I think we can keep the question for the discussion session.
Yeah, sure. Thank you.
Yeah. Let me introduce the next speaker, which is the let me see. Okay. Here it is. Here it is. So the next speaker is the Professor Shaoying Huang from Singapore University of the Technology and Design. And then for her quick bio, is the Professor Shaoying Huang is an associate professor in Singapore University of Technology and Design. She's an adjunct associate professor in the Department of Surgery in National University of Singapore in Singapore. She has received her PhD degree from Nanyang Technological University and MIT in 2011. Her background is electromagnetic and then electromagnetics and electromagnetic compatibility, and she is one of the pioneers who pushes towards the innovation on the MRI hardware to make MRI portable and accessible. She has owned 8 patent and 6 technology disclosures and numerous reports, journal papers at the international conference papers. Okay, so without further ado, please, Professor Huang, to get started for your talk.
Thank you for the introduction, Mitch, and thank you for having me. So let me share my screen. So today, I will be sharing additive printing for portable MI. First of all, I'm not expert of 3D printing, but I'll share with you my experience on how we use 3D printing for portable MI. So this is the mission of my research group, which is based on electromagnetics. We try to push the boundary of knowledge for MedTech and innovate solutions for MedTech. And this is a landscape of research activity in my research group, including the portable MRI, also MRI safety, for high field MRI, and as well as reconstruct electrical property based on data from MRI scanner, which is the B1 maps. And we also work with the industry by innovate for non-contact in-circuit testing, also doing wireless power transfer for human-centric kind of environment, new material for antenna miniaturization, as well as non-invasive glucose sensing and additive printing for high-frequency application, mainly focusing on paper-based aerosol jet printing. So for MRI, we know its advantages mainly is the non-invasiveness as well as non-ionizing radiation, and it offers the best tissue contrast. Here shows briefly how MRI works. So to make MRI work, our human body has 70% of water. So we have abundance of hydrogen molecules here. So to make it work, we need to polarize all these spins, the atoms inside our human body using magnet, which is the 3T or 1.5T MR scanner that we're talking about, how much Tesla. And this also associated with how much of magnetization that we can have that's associated with the numbers of nuclear inside the human body, etc. And then we do the precession using radio frequency coils, and the magnetic field is dynamic right here compared to the magnetic field offered by the magnet, which is static. Then the working frequency of this radio frequency coil is related to the static magnetic field that we talked about just now, and the frequency here is called Lamont frequency. And then we also need the gradient coil to do encoding and the readout. Here, pretty much is like register each atoms where the signal comes from, so that when we receive the signal, we can map it back and know that and do the distribution. So we can have the structure of the inner structure of a human body by just manipulating the signal that we receive from the hardware. So with that, MRI also has its pain point. The first pain point is bulkiness. So it can't really afford, and we can't really afford the imaging at places like ICU or after a disaster that we want to do the rescue, because a normal traditional MRI takes 3 rooms, 1 magnet room, and then 1 control room and 1 equipment room. And meanwhile, it's expensive, so it has high acquisition cost as well as operating cost. So for underdeveloped countries or regions, it's really hard to afford. For this reason, there are 70% of the world population can't really have the MRI scans when they need one. So now if we focus on portable MRI, then the focus here is low field MRI, which the field strength we're talking about is about 10 millitesla to 1 Tesla. So it enjoy all the advantages of, for example, like it's open, it's not like putting the human body inside the tunnel, and then it's compact, it has a small 5 Gauss zone. So the 5 Gauss zone here means that outside the zone is very safe to put any metal, for example, like pacemaker or scissors, etc. So a smaller 5 Gauss zone will make the machine very compatible to a lot of locations, for example, like an ambulance. And it also has the improved safety, for example, low specific absorption rate, which is the parameter that we use to quantify how much radiation from radio frequency wave a human body will absorb. And also the heating effect is low. And meanwhile, the low field, the benefit it will introduce is also less artifacts from the implants. And with this, it may lead to simplified hardware and therefore portability and low cost. So if we think about how magnetic field is offered in an MRI scanner, there are 3 ways based on our knowledge from high school. One is the superconducting magnet, and when the coil that is not in a superconducting state, then we have resistive magnet, where the resistance of the coil is relatively high. And meanwhile, we also have the permanent magnet. So for superconducting magnet, it takes an expensive refrigerator to maintain the superconducting state. Therefore, there's a high power consumption associated, and that cooling system, that refrigerator, so-called, is super sophisticated. So it's also power hungry. And for this part, this kind of MRI scanner for low field, that's normally is greater than 0.5 Tesla. And there's one product that's in this domain, which is the 0.55T Siemens system that is launched a few years back. And for resistive magnet right here, as it doesn't take complicated cooling system, so the power consumption associated with it is also much lower. But for resistive magnet, there's no refrigerator that is helping to cool down the system so that the amount of current is constrained, and therefore the field strength is also constrained. Normally, the magnetic field that it can offer is less than 10 millitesla. And there's one example, which is a lab setup in Matthew Rosen's lab in Massachusetts General Hospital. The magnetic field there is a 6.5 millitesla for head imaging. And for permanent magnet is that kind of rocks that we prepolarize it so that it carry the energy cell and it carry the magnetic field. So there's no power consumption associated with that, and we don't need a cooling system for system based on permanent magnet. And normally the magnetic field that it offers between 10 millitesla to 0.5 Tesla, and it lead to portability that I'll explain later. So back to superconducting magnet, this the novel kind of set up in a research lab in University of Minnesota. They have a set-up kind of magnetic field. So for this system is head only, and it's quadrant-free. It has a relatively small 5 Gauss line compared to a traditional system, and the weight of the magnet here is about 600 kilogram. And if we compare a traditional system to a portable system side by side right here, one main thing here is the portable system is body part dedicated, which means that when we want to image the head, we build hardware around the head. And if we want to image the knee, we build hardware around the knee. That's the dedication that we're talking about here. And meanwhile, like what I mentioned just now, permanent magnets are used. So it carries its own energy. It's not power hungry. So for permanent magnet, originally we have this traditional C-shape and H-shape magnet that's popular in the history. And recently, with all the effort for portable MRI, there are sparse magnet array like Hobart cylinder, Hobart sphere, and inward-outward ring, which is the magnet array that my research group has been proposed and pushing forward for portable MRI. And back to the C-shape, H-shape, it's usually dense and is relatively heavy. So it's still can be very portable. But for Hobart and inward-outward ring right here, it can be sparse and it can be lightweight as well. So for C-shape, H-shape, there's systems, and if we apply the body part dedicated right here. So here is the L-Celta, the knee scanner from L-Celta Italian company. So you can see that the 5 Gauss zone is much smaller. And there's also another example from Jiangsu Lizi, which is a baby head MRI. So it has a field of view of about 15 centimeter diameter in spherical volume, DSP in short right here. And you can see the 5 Gauss zone is also much smaller. It's a half a loom size. And there's a lab-based kind of system from Tsukuba University in Japan. They have a system, has a field of view of an ellipsoidal kind of field of view, about 15 centimeters as well, for elbow scans with the field strength of about 0.3 Tesla. And recently, for the C-shape and H-shape, that is the portable head MRI, which is from a company called Hyperfine. So for a system like that, is the field strength is about 64 millitesla, and the 5 Gauss zone is about a diameter range, a range with a diameter of 1.6 meter, and the weight is more than 500 kilograms. And there's a similar lab-based system from Hong Kong U, where they demonstrate using AI for denoising, and the magnet that they use there is 750 kilogram, which is relatively heavy. And so for the sparse magnet array that I mentioned just now, there's a system for HUANG, which is a sparse magnet array that you can see from Leiden University from Netherlands. So a magnet like that offer a magnetic field of about 50 millitesla with homogeneity. And there's also another system from Massachusetts General Hospital that using the magnet, the configuration sparse magnet, they offer linear gradient in the vertical directions, you can see, for encoding. So, and another system that is similar to that, also the Hobart cylinder array, it has a built-in gradient, but the gradient right here is nonlinear for encoding. And for Hobart sphere, there's a hemisphere structure, which is at 64 millitesla for prostate intervention. So this is a product from California. And for the inward-outward ring, this shows the prototype that we had in the lab that offer linear built-in gradient. So this inward-outward ring, as you can see right here, the magnetic field, rather than being pointing in the transversal direction, is pointing in the longitudinal direction. So it's pointing in the same direction as most of the MRI that we have nowadays. So the technology that we developed for the MRI that nowadays can be directly applied to the system, the magnet that we build. And meanwhile, it has a space in between the rings, so it allows intervention. And here, there's other advantages of it. For example, it has useful variants. For example, if it's a half sphere, it allows high performance, that kind of magnetic field that can scan spines. And it has a very small 5 Gauss line, means that it's very safe to be sighted in a small room. And all this, our design is supported by an in-house built tool called Matrix. So it has fast calculation. It can afford the calculation of multi-millions of magnet at the same time. So we can guarantee the high performance of the magnet array, yet keep the weight light. And here shows our another kind of technology that we can shield the whole scanner easily. So if you compare the two columns right here, one is without the shooting techniques and the other one with our shooting techniques. So the photo here shows exactly how a scan is done. You can see that there's no shooting room, there's no shooting box or any shooting blanket, but we can suppress the noise effectively. And these are the different iterations of prototype that we have in the lab, and then we can scan head and knees for now. Yeah, and this summarize the performance of the head scanner as well as the knee scanner, the weight as well as the resolution. And the system like that is aimed to supplement the current system rather than replace them. So you can see build an MI system, we need magnet, we need the RF coil, as well as gradient coil, and then spectrometer, pulse sequence programming, and image reconstruction. And here, the role of 3D printing in gradient coil design is such. So we know that the gradient coil is used for encoding and for readout. And here on the photo on the right give us a more direct kind of illustration how important is a gradient. But traditionally, this is how a gradient is done, which is very labor intensive. And on the right hand side is a 3D printed ones that we did in the lab for lab magnet. So the design tool is quite available, including open source, for example, like CoilGen, and it allows coil optimization, including its electromagnetic properties like resistance and inductance and coupling as well. And the parameter that you can define, including coil radius, length, and diameter of the grooves, and the structure of the interconnection of wires, etc. So traditionally, like what I showed just now, so pretty much, right, is a very time-consuming and complex winding process of the wire onto the housing, for example, like fiberglass, and then coat it with epoxy resin, etc. And it limits the custom-made kind of coil design. But the advantage that the 3D printing can offer is how easy it can be customized the coil design, and then we can immediately turn it into a housing structure as well as the corresponding wiring. And that also allows complex design, including cylindrical or planar kind of design, and the design can be easily revised at the 3D printing software. And better yet, right, a process that we came up with is the group with kind of grabbing capability right here, so that we can even remove the process of using glue gun. So just grab it automatically by using playing with the property of the material, so that the populating of the wire onto the housing become very straightforward and less labor intensive. So it helps us to achieve different kind of geometries, and the material that we use really allowed an easy plastic joining, as well as if we use glue gun, is also very thermal friendly. Yeah. So here shows the approach that we have nowadays. Pretty much when we come up with a design, we split them into multiple sections, so that these multiple sections can be printed simultaneously in parallel. So after that, we glue them together as a whole long cylinder for populating the wire. And the next part is about the ARC coil design, which is for precision as well as for signal acquisition right here. So originally, the traditional method of construction and ARC coil is also time-consuming, and it leads to inevitable assembly deviation, as well as high manufacturing cost. But 3D printing really gives us advantages of low cost and fast speed, as well as high accuracy in the following way. So it's very customizable, and then even for very complicated structure like this, the AI assisted kind of design solenoid coil, that it has very kind of optimized complicated pitching compared to a traditional solenoid. And in terms of material, it becomes very flexible for us to have both the base as well as the grabbing structure, so that we can populate the wire, and it reduces the time and cost a lot and increase the precision a lot, pretty much like what the gradient coil would give us. So this shows how the coil can be populated onto the housing. Yeah. And here shows measurement as well as simulated result. As you can see, comparing to the measurement result to the simulated result, due to the high accuracy of coil building, it gives us a good agreement between the simulated result and the measurement result. Yeah. So for low field and portable MI, if we look forward, right? So how that will affect us, it really because it's modular and it can offer on-site in-time kind of imaging, easy to operate, and allow remote diagnosis and compatibility with telemedicine. So if we take a look, right, the medical need for ICU, for moving platform, hard to reach area, disaster rescue, battlefield, it will be helpful, and it will also be helpful to decentralize the MR scanner and move it out of the radiology department to other departments in the near future, as well as clinic. Yeah, so it will shorten the waiting time and timing, so offer timely diagnosis and better resource allocation in terms of the whole healthcare. So it will also allow routine scans to form to lead to informed healthcare, early detections, and early treatment, and allows longitudinal study of the brain, especially it will be meaningful for an aging brain. And for this, we also step one more step further. So in terms of have all this technology more accessible, we try to make it the accessibility of technology will make the field progress faster towards clinical viability and prepare for the technical support in the resource scarce region when MI become available. So this is pretty much a hackathon that we did recently to promote the technology. So within 3 days, we built an MRI head scanner, and the participants is come from 14 countries. Yeah, with that, then yeah, thank you for your attention.
Okay, thank you very much, Professor Huang, for the amazing talk. This is a very nice application of the 3D printing for the medical devices. So, right, so now, since we had a two talk, we would like to, let me come back to the slide once again. Okay, so let's move on to the panel discussion. Then here I'm going to introduce the Professor Kong from Shenzhen University, and then let me briefly introduce Professor Kong. Professor Kong Tiantian is currently a professor in the Department of Biomedical Engineering at Shenzhen University in Guangdong Province in China. Current research interests includes microfluidics, soft matter, conservates, organ on chip, and 3D bioprinting and biomaterials. Okay. Dr. Tian Tian Kong received her Master of Science and PhD degrees from University of Hong Kong in 2009 and 14, respectively. After 1 year of postdoctoral training at the same institution, she joined the Department of Biomedical Engineering at Shenzhen University in November in 2015. Initially as an assistant professor before being promoted to the current positions. Okay. As the first and corresponding author, she has published more than 17 papers in the high-impact journals, including Nature Communications, ENAS, Advanced Materials, and Advanced Chemistry. Okay. So additionally, her work has been featured in Science News. She has served as the multiple editorial positions, including the microengineering and nanosystems, green energy environment, and small. Okay. So please welcome Dr. Tian Tian Kong as a panelist for this discussion. So yeah. So here's it's going to be the bit of the open discussion. I think we can take the questions if there are any from the audience, as well as we can probably starts the general discussion of the 3D printing. So maybe the first I would like to ask all those speakers and the panelists. Maybe perhaps each of you have a different field of the 3D printing. And then what is the currently the major the theme, major big topic of the 3D printing in your own field? If you can elaborate a bit more. So perhaps may I start asking the Professor Chen? Could you please comment on the what would be the major the topics or major problems in the field of the ceramic 3D printing?
Okay, thank you. Sorry, I do not know how to pronounce your name again. Dao Shang. All right, Professor Dao Shang. Thank you very much for your question. Yeah, so you are asking that the major progress in the ceramic field for 3D printing. I think although it's a very narrow field, people not often know that 3D printing can be used for ceramics as well. And we still do some sort of progress, especially nowadays. 4D printing is is kind of hot topic, especially in terms of polymers and also the alloys, metallic components. They all have a sort of progress in terms of 4D printing. That's another dimension, like a time dimension, apart from the 3 XYZ direct dimension for the space. So 4-dimension or 4D printing for ceramic, they are largely depend on the elasticity and the plasticity of the material itself. But here, it's very hard for the ceramic components to be deformed largely with the large displacement. That's not possible way. So what about 4D printing? We do with the polymer derived ceramics, then 4D printing can be possible. We deform the shape before the precursor becomes ceramics. So it will be sort of a polymer based material. We call it pre-ceramic polymer or precursor ceramic or something similar terms we can call it. So before the transformation into ceramics, 4D printing can be possible for the precursors. So 4D printing, if that's possible for ceramics, then there will be many types of applications we can do, especially for the aerospace exploration, and we need to save space. So we try with the similar procedure for the polymer shape memory effect and so on. Then you can design and packaging quite well the ceramic components inside a limited space. Then for the exploration, and there's another application is for the laptop, also for the mobile phone, smartphone. Now there's a foldable smartphone. And the foldable smartphone, we normally use a kind of sort of mechanism to manipulate with the folding. Then if we can do 4D printing with ceramics, then it's easy to have a case made by ceramic for the folding phone, the foldable phone. And there will be no longer, because when you're using ceramics, there's no longer possible way of the shielding of kind of signal, because inorganic materials, there's a very nice transformation with the wireless or kind of signal transmission, and that's a benefit from ceramic. And the foldable phone can be realizable by using 4D printing as well. So these are some of the major progress. And I mean, for the time being, it's still not too much known by other people, but we're still working hard. And maybe in the future, we can do something with the 4D printing for the ceramic components. That's my answer. Thank you very much.
Oh, thank you very much, Professor Chen, for the amazing insights. So I think how about Professor Huang? Would you be able to comment on the how you can what could be the one of the big problems of the applying 3D printing in your own research field, such as MRI devices?
I think it will be very interesting to see that whether we could just 3D print the whole MRI scanner out of it, because within 3 days, right, we built an MRI scanner, but it's like using hands and then mixed with 3D printer, 3D printing and hands. So yeah, if a scanner can be just print out of it, that would be fantastic. So that is kind of like we have a design, and then the next day you can scan your hand. Yeah.
I see. That's very interesting. Perhaps, what is missing? What is still the gap between the the printing MRI scanner with the status quo? What has been the research gap or technology gap that has been preventing to get to there?
I'm not sure whether there's a gap because maybe it's just because I didn't know, right? But I would imagine that there's a need, which is the mixed kind of material. For example, like just now, Professor Zhang mentioned, right? If so, ceramic printing can mix nicely with metal printing, so that we could immediately print whatever capacitor that we want. And then after the printing of a capacitor, then we can print the coil and with there's some supporting structure immediately. So that would be something that is interesting to see. But another thing is the printing, right? We need to do it up to a scale that it can be around at least a human head or human hand. So that is a bigger scale. It's not like a miniaturized scale of printing. Yeah, we need a bigger scale than the printing. So one is the size, and then the second thing is the compatibility of all the material together, and one after another, maybe sequentially and in parallel. Yeah.
Okay. Well, thank you very much. I think that, thank you very much for your insights, Professor Huang. Then, let me ask Professor Kong. I think Professor Kong is from the field of the biomaterials and bioprinting. I mean, in your own research field, Professor Kong, what do you think is the major progress currently, or major, the problems that the research field is facing?
I think the most promising application in the field of bioprinting is to actually print tissues and organs. But now we are still very far away from 3D printing a fully functional organs for transplantation. But there has been significant progresses in creating tissue constructs that can be used for drug testing, disease modeling, and eventually regenerative medicine. So there has been a lot of progresses in organs on the chip and organoids on the chip, and also some of the combination of bioprinting and the software robotics has the potential to create biohybrid robotics or devices that can be used for minimal invasive surgeries or therapeutic applications. So these are very exciting and potential developments.
I see. Okay. Well, thank you very much for your insights, Professor Kong. I guess, since I have been asking, I also, I'm also from the 3D printing research field. If I comment something on maybe, I also work on the bit of the bioprinting and then microfluidics, but perhaps what makes us maybe, different in this group is I also work on the 3D food printing, which is 3D printing of the edible materials. So I think, I'm very excited to work on this research fields because, there are many different opportunities. For example, the designing the texture of the food. The texture, designing a texture has been extensively done with the different type of 3D printing method. But, if we are able to design the, texture of the food, for example, we can potentially develop the different food materials with the different health impact, positive health outcome. For example, the people has been working on the 3D printed food to sort of, to create food materials that is tailored for the people who has the difficulty in swallowing food materials, such as dysphagia. Okay, that would be one potential things. Another thing is the always people talk about the personalized nutrition. So depending on the people's needs, one of the advantage of the 3D printing is you are making the materials or structures one by one, and then this is really great technologies to try to develop something that has the positive health outcome, which is tailored for the individuals. So I believe 3D printing when it is applied for the I think food and nutrition, there would be another big opportunities. That is something that our research group is also looking at. So this is just my comment here. The so I guess it is great group of the people. All of us has a different expertise, and then all a bit different. There's some overlap, but many different. The research fields seems like there's a big many different opportunities. So, maybe perhaps, regarding the opportunities, what would be really the new opportunities, whether this can be a fundamental research or, the industrial opportunities, perhaps would you be able to give your insights about what would be the upcoming different opportunities in your research field. I mean, whether this is the bring the big money, or whether this is bring the people's health. I mean, improve the people's the health, for example. Could you please comment on what can be the next big opportunities, and then the people should be looking at in the field of 3D printing, which is especially relevant to your research field. Would anybody be able to start?
Maybe I can get started. So I think one thing I can imagine is if the 3D printing, the whole MR scanner can be done, then we're free. Then we can really allow a lot of area to have 3D to have a portable MRI. So you could just loan the machine and then print. Just pay for the material, so it will become cheaper.
I see. But I mean, maybe if I ask to be able to realize the 3D MRI, portable MRI, I think the different kind of materials must be being printed, right?
Yeah.
Is there any the particular materials, type of materials that can be really important or useful to be 3D printed in your field to develop different type of the medical devices or MRI?
I can't answer this right now.
Perhaps, yeah, okay. Well, that's I guess I naively said, we probably need to advance the for example, the electronic circuit printing, metal printing, electronic
Yeah.
printing might be, yes, there are technologies, but whether this is going to be fast and then, demonstrate, things fabrication much more quickly. I think that there's be some research, the gap or the research opportunities which could be potentially help the field. I mean, well, I just saw. I mean, this might be one of the my own thoughts, but yeah, this is just my comment here. But oh, thank you very much, Professor Huang. The Do you have any comment about opportunities, or the research opportunities in your own research field, Professor Chen? Do you have any comment on that? How ceramic printing, is going to, develop, say, like, in the next 5 years and 10 years?
I think I always emphasize that 3D printing ceramics is more or less like a narrow field, and people not really know much about it. But as I previously discussed in my slides, that we do show some sort of very significant example, like we make some progress in the nuclear fusion reactor for the treating breathing, and that is in my opinion is kind of significant application side, and especially for energy relevant, like nuclear fusion. And we also do some sort of 3D printing inorganic material for lithium-ion battery and solid oxide fuel cell. All these kind of three applications, they are all relevant to energy, resources, green energy, the future energy topics. So the 3D printing, especially in terms of ceramic field, I would mostly put my effort in the energy sector. So that's much relevant to what I'm working on. But I pretty much agree with Professor Kuhn said that, especially for bio printing, bioprinting. My idea is, there's a Chinese fairy tale, 神笔马良. So it means that if you use a magic brush, you can paint it and paint anything you want it. So it means that what you print is what you get. So it means that if in the future you can print your organs, print your any type of any parts of your body, then you do the transplantation. Then it will be easier for customization and easier for the time saving and so on. So lots of things can happen when you can print whatever you want. in the near future, then that's something, I mean, in the medical field, but that's not too much relevant to the ceramic thing. But I do believe that I'm more interested when it comes to reality for the organ printing. But still now it's not possible. We just do the lab scale researches on the, for the tissue engineering, for the printing of some sort of cells, tissues, biomedical engineering, and so on. But that's far from the reality. I mean, far from the future dream. What we want is the entire fully functional organs that we can get for the transplantation. That's something I really want. Especially Professor Kuhn needs to work on that field. Yeah, thank you.
Thank you. Yeah, thank you very much, Professor Chen, for your insights. I guess we talk about the organ printing and such. Professor Kong, do you have any comment on on those technologies or anything else that you do believe that's is coming? The next opportunities in this research field.
I think organoids are very hot right now, and there's many drug companies who are very interested in creating miniaturized tissue models such as liver, kidney, to test the efficiency and safety of new drugs or screen drugs for cancer patients. And I think this is a very good opportunity. Another opportunity for bioprinting, I think that will bring in a lot of money, is the creation of patient-specific implants, such as bone scaffolds embedded with sensors, and dental implants, or the dental veneers. That's a porcelain that will stick on the surface of the teeth that can improve how your teeth looks. I think that's that will bring a lot of money. Yes. Actually, I have one question for Professor Chen. Because I saw Professor Chen do a lot of 3D printing of the inorganic materials for energy storage systems. I was wondering what 3D printing can do for improving the performance of like capacitors or batteries. I don't quite because I don't quite familiar with that. I was wondering how 3D printing can improve the performance of energy storage systems.
Yeah, thank you for the question. It's a nice question, actually. I think I have shown you the very later stage of my presentation. There will be there were some sort of few slides showing what we were doing regarding the SOFC, solid oxide fuel cell, and the lithium-ion battery. And the aim is increase the the power density and capacity and so on, electrochemistry performance. So what we do is using a low temperature direct writing procedure on the kind of machine we build in our own lab, and the procedure is like we create much more space inside these kind of 3D printed structures. So the microstructures for the 3D printed structures, it's much better than conventionally like roller coating and other types of conventional technologies, because using 3D printing, we will possibly create much more porosity inside these kind of components. So that there will be larger interchange of the ions inside this kind of porosities, and that as a result, their electrochemical performance can be enhanced. So this is one thing, and another thing is for example, for the SOFC fuel cell components, we need a thicker or even like uniformer sort of porosity. And using 3D printing, you can design and create the what we call it customize or not, but it's kind of customization. Then you can create your designed microstructure very easily, because using conventional procedures, the only thing can manipulate is the sintering. The temperature, you can only change the temperature. There's no possible way to directly design and place the porosity and allocate the porosities differently within the structure. So with the 3D printing, that can be possible. And based on all these, the creation of porosity, manually control porosity, then it's easily for you can increase the electrochemical performance for both batteries, and also the fuel cells. That's my answer. Okay. I don't know if you can get my ideas.
Oh, this is great. Yeah. Thank you very much for the question, Professor Kong, and thank you very much for the answer, Professor Chang. I believe some of you. I mean, I guess with from your answers, I believe this 3D printing is really close to the industry. I believe, and there's many opportunities for the commercialization of each of the technology, whether this is inorganics or the biomaterials or the medical devices. Perhaps would you be able to comment briefly on the what is your thought on the different type of commercialization opportunities of your research fields of the 3D printing? Anybody, if you have opinions?
Maybe I can start firstly
Yeah, sure.
answer your question, especially for because we work very closely with industry, like basically in China, especially for the ceramic industry, and the people more working on the powder side, I mean the material side, and also there are, if that's something relevant to 3D printing, that will be the equipment. There are many companies working on the equipment, especially for ceramics. They produce their equipment and sell equipment to the universities and institutions and so on. They are not really like commercialized as a larger scale, like a factory. No, so they sell small batches of equipment devices to the labs, and not really industry, and that's something they can make money. But this is because I mean, as I always stress on this, so this is difficulty for the commercialization of 3D printing ceramics. There's not much useful applications for 3D printing of ceramics. That's something come out from the current situation. So people are working hard for the material side and also the equipment side, but not really too much effort for the application side, because that's not that mature than the hardware and also the materials. So that's something I can see from the 3D printing of ceramic industry. Okay. Yeah.
Thank you.
So commercialization only on materials and also the equipment, not on the application side for ceramics. Not yet. All right. That's my observation. Thank you.
Okay. Yeah, thank you very much. This is very insightful. If you have any comment, would you have any comment, Professor Huang or Professor Kong?
Okay. So maybe I so I think currently for 3D bioprinting, it's a similar situation. For ceramic printing, there's at least in China, I think there are more companies who are selling bioprinter and bioinks instead of direct applications. There are companies of organ chips, organoids, but these companies are selling reagents like the culture medium, the materials to fabricate organ on chips, etc. So I think companies, there are also companies who commercializing bioprinted implants. That's basically in dentistry and orthopedics. Yeah.
I see. That's great. I believe I think right now this is the materials and the instruments, but I'm pretty sure once this field is going to mature more, there should be a lot of opportunities for the I guess personalized the medicine for the by bioprinting. I believe. I think this is a great, very exciting field. The Do you have any comment, Professor Huang, about the MRI? I mean, doesn't have to be MRI, but
Medical devices?
Yeah, medical devices in general. Yeah.
I think 3D printing can really help to democratize the technology a lot. Yeah. So back then, without 3D printing, right, a lot of things it's expensive and only available to the big guys. Yeah, but nowadays it becomes so easy to access. So with that kind of accessibility will encourage more people, and even for like students, they can really afford and play with it. So it really help with that. And then it will train more people with knowledge in this domain so that it will accelerate the whole the growth of the whole area. Yeah.
I see. Okay. Well, thank you very much for your comments. I think okay, yeah, we have very nice discussion, and then so I think this is the great discussion, and then perhaps due to the time we can probably wrap up. I think you can give one comment about your passion or the about your love and passion to the 3D printing, and then we can conclude this discussion. I think the Professor Chen, do you have any comment? Just one very simple comment about the excitement about 3D printing.
Well, I think I have a supplementary comments succeeding Professor Kuhn's opinion is that 3D printing only in the the potential application side, not only in the energy sectors but also in healthcare, like the dentures, as Professor Kuhn mentioned earlier. We are working also for the crowns and for the teeth. There are three parts teeth we can make using ceramic like zirconia, alumina. So these can be a high profit. So we can make money in the future for that kind of industrialization or commercialization. So I'm sort of optimistic regarding the 3D printing of ceramics. Otherwise, I cannot sit here sharing with you guys on 3D printing of ceramics. So I still quite believing that 3D printing ceramics have a bright future, and that's something I want to say. Thank you. Thank you very much.
Professor Huang?
So for 3D printing, I see it as a tool that it really help with the democratization of the MI technology. Yeah, that's fantastic. It's been fantastic so far. Yeah.
Thank you. So finally, Professor Kong, do you have any comments?
Yeah, I think we are still like dreaming one day we can print a functional tissue or organs, and that's really exciting and really something worth to work for.
Hey, wow, this is great. I think thank you very much for your very encouraging comment. I think I believe many students are listening to our talk, and then I believe the students they are going to be they be excited to enter in this field, and then we are going to work all together. So just to conclude this this session. Thank you very much. This is the the quick certificate for the Professor Chen Zhangwei from Shenzhen University. Thank you very much for your talk on the 3D printing of inorganic material. And thank you very much to the Professor Shaoying Huang from Singapore University of Technology and Design about your talk on the additive manufacturing, additive printing for the portable magnetic resonance imaging. And then, of course, thank you very much, Professor Kong, for joining our in the panel discussion. So just to the last slide. So this is a slide. We are going to have the another session next week on the September 17th, Tuesday. And then this is going to be on the topic of the physical and the digital fringe technology. Okay, so we are thank you very much for everybody for listening our talk today. And then we are looking forward to seeing you all in the next week. Thank you very much. And then this concludes our session today.